Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Lars Onsager's 1944 Nobel lecture, titled Reciprocal Relations in Irreversible Processes, represents a moment of profound synthesis in the physical sciences, delivered as a clarification and celebration of his seminal 1931 papers. The lecture itself stands as a distinct intellectual artifact, a carefully constructed argument designed to persuade the sophisticated audience of the deep connections between the time-symmetric world of microscopic mechanics and the time-asymmetric reality of macroscopic dissipation. This essay undertakes a rigorous internal evaluation of the claims presented within that 1944 exposition. It will proceed by systematically analysing the logical and conceptual pillars of Onsager's argument as he laid them out, examining the coherence of his postulates, the strength of his derivations, and the explanatory power of his conclusions. The inquiry will focus exclusively on the internal architecture of the lecture, tracing the path from its foundational physical intuitions to its celebrated mathematical results and their empirical validations, thereby assessing the work on its own formidable terms. Section 1. The foundational postulate of microscopic reversibility. The lecture commences by anchoring its entire theoretical edifice to a single, powerful principle: microscopic reversibility. Onsager's claim here is that the fundamental equations of motion governing individual particles, whether classical or quantum, possess high reversal symmetry. An immediate evaluation of this starting point reveals its strategic brilliance. He is building his theory of irreversible, energy-dissipating processes upon a bedrock of perfectly reversible mechanics. The argument he presents posits that if one were to record the motions of all particles in a system and play the recording backward, the resulting physical behaviour would be equally valid according to the laws of mechanics. A collision viewed in reverse is still a valid collision. Onsager uses this principle to make a statistical argument of profound consequence. He considers the time correlation function between two fluctuating macroscopic variables, for instance, the deviation of temperature in two different locations from their equilibrium values. He claims that the average product of the first variable at a certain time and the second variable, a short interval later, is identical to the average product of the second variable at that certain time and the first variable the same interval later. This claim, expressed as the expectation value of the quantity alpha sub I at time t multiplied by alpha sub k at time t plus time step tau, is equal to the expectation value of alpha sub k at time t multiplied by alpha sub I at time t plus tau, is a direct consequence of tie reversal symmetry at the microscopic level. The strength of this initial step resides in its elegant appropriation of a well-established concept from fundamental physics for a new purpose. He asserting that the symmetries governing the unseen world of particles impose strict constraints on the observable behaviour of the collective system, a connection that forms the very soul of his entire project. Section 2. The linear phenomenological laws. Having established his microscopic foundation, Onsager proceeds to the macroscopic description of irreversible processes. He claims that for systems sufficiently close to equilibrium, the rate of change of a macroscopic variable, which he terms a flux, is a linear function of the thermodynamic forces driving it. This is presented through a set of equations where each flux, denoted by the symbol J sub I, is expressed as a sum over all relevant forces, x sub k, with each force being multiplied by a phenomenological coefficient, L sub ik. A critical evaluation of this claim reveals it to be a linearization, a pragmatic and powerful approximation. The assertion relies on the idea that for small deviations from equilibrium, any more complex functional relationship can be effectively represented by the first term of its Taylor series expansion. The force, x sub k, is itself defined carefully as the partial derivative of the system's entropy with respect to the corresponding state variable, alpha sub k. This formulation accomplishes two things. First, it provides a concrete, operationally defined mathematical structure for describing coupled phenomena, such as a heat flux being influenced by both a temperature gradient and a concentration gradient. Second, it limits the immediate domain of the theory's applicability. The framework's validity is explicitly contained within the near equilibrium regime. Onsager's argument here is one of practical physics. He is developing a tool for a specific, yet widely applicable, set of physical circumstances. The power of this claim lies in its ability to translate the complex, multifaceted nature of transport phenomena into a manageable system of linear algebra, a move that renders the problem amenable to a general solution. This section of the lecture functions as the construction of the macroscopic stage upon which the consequences of microscopic symmetry will play out. Section 3. The principle of the regression of fluctuations. The intellectual core of Onsager's entire lecture is presented in his hypothesis concerning the behavior of spontaneous fluctuations. This is perhaps his most audacious and insightful claim. He posits that the decay of a naturally occurring microscopic fluctuation from equilibrium follows, on average, the same macroscopic phenomenological laws that govern a relaxation of an externally induced imbalance of the same magnitude. In other words, the way a system returns to equilibrium after being momentarily perturbed by its own internal thermal noise is indistinguishable from the way it returns to equilibrium after being given a small, deliberate push. This principle of the regression of fluctuations forges the crucial link between the statistical mechanics of noise and the thermodynamics of transport. Critical assessment of this claim must recognize it as a postulate, a statement of physical intuition whose justification lies in its immense predictive success. Within the lecture, Onsager presents this idea as a natural extension of the work of Einstein and Smoluchowski on Brownian motion, where the same random forces that cause a particle to wander also give rise to the frictional drag that resists its motion. The strength of the claim is its profound implication one can learn about a system's deterministic response to external forces by observing its random, internal chatter. It equates the dynamics of spontaneous and induced processes. This is a conceptual leap of the highest order, allowing him to use the time correlation functions derived from microscopic reversibility to make statements about the macroscopic coefficients, the L-subic values, that appear in his linear laws. The entire edifice of his reciprocal relations rests upon the validity of this single, elegant hypothesis. Section 4. The derivation of the reciprocal relations. With the three main components in place: microscopic reversibility, linear phenomenological laws, and the regression of fluctuations, Onsager proceeds to the lecture's central derivation. He aims to prove his primary claim: the matrix of phenomenological coefficients is symmetric. Specifically, the coefficient L sub ig, which quantifies the effect of the force x sub k on the flux J sub I, is identical to the coefficient L sub chi, which quantifies the effect of the force x sub I on the flux J sub k. The logical chain of his argument is masterful. He begins with the time correlation of two fluctuating variables, alpha sub I and alpha sub k, and uses the regression hypothesis to relate their average behavior to the macroscopic fluxes. He then uses the linear laws to express these fluxes in terms of the forces and the L coefficients. By combining these steps with his initial statement on the symmetry of the time correlation function derived from microscopic reversibility, the conclusion becomes nearly inescapable. The derivation essentially translates the microscopic time symmetry into a macroscopic symmetry of coupling coefficients. An evaluation of this derivation reveals its formal elegance and logical coherence. Each step follows from the previous one, building an airtight case based on his initial postulates. The claim is that reciprocity is a universal law for near equilibrium transport processes, as fundamental as the conservation of energy. There is a certain intellectual satisfaction in seeing the disparate pieces click into place, a testament to the power of a theory built on deep physical principles. The derivation itself is the climax of the lecture, a moment where abstract symmetries are shown to have concrete, calculable consequences for real-world phenomena. Section 5. The role of external magnetic fields and Coriolis forces, a mark of a truly robust theory. is its ability to account for apparent exceptions and to refine its own rules. Onsager demonstrates this by addressing the influence of external forces that themselves behave differently under time reversal, such as magnetic fields and Coriolis forces. His claim here is a modification of his central result. In presence of a magnetic field, B, or an angular velocity, omega, the simple symmetry of the coefficients is broken. The new relation he proposes is that the coefficient L sub ik, evaluated in the presence of the field B, is equal to the coefficient L sub chi, evaluated under the condition of a reversed field, negative B. In spoken form, the relation is L sub ik of B equals L sub chi of negative B. This claim is a profound statement about the deep structure of the theory. It shows that the symmetry of the phenomenological coefficients is directly tied to the symmetry of the underlying physical laws governing the microscopic motion, since the Lorentz force, which governs particle motion in a magnetic field, depends on the direction of the field. The macroscopic transport coefficients must reflect this dependency. Critically evaluating this section showcases the theory's subtlety and depth. It is a self-consistent framework. The modification is not an ad hoc fix. It emerges directly from a more careful application of the principle of microscopic reversibility to systems whose fundamental dynamics are altered by the external field. This refinement significantly broadens the theory's applicability, allowing it to correctly describe phenomena like the Hall effect and other galvanomagnetic and thermomagnetic effects, where such asymmetries are the defining characteristic. Section 6: Illustrative Applications and Experimental Corollaries. The final section of Onsager's argumentative structure within the lecture is dedicated to demonstrating the practical power of his derived relations. He moves from abstract principles to concrete physical examples, with a particular focus on thermoelectricity. His central claim in this segment is that long-observed empirical relationships, previously understood only through specific and sometimes tenuous thermodynamic arguments, are in fact direct and necessary consequences of his general reciprocity principle. He revisits the work of Lord Kelvin on thermoelectric effects. Kelvin had shown, using a thermodynamic cycle argument of some controversy, that a relationship should exist between the Seebeck effect, where a temperature difference creates a voltage, and the Peltier effect, where an electric current generates a heat flow. This relationship, known as Kelvin's second relation, is elegantly derived as a straightforward result of Onsager's reciprocity. By correctly identifying the conjugate fluxes and forces for heat and charge transport, the equality of the Seebeck and Peltier coefficients emerges directly from the L sub ik equals L sub chi relation. Evaluating this claim serves as the ultimate validation of the entire theoretical structure. The theory is shown to subsume and explain previously isolated empirical laws, placing them within a unified and fundamental framework. He performs a similar analysis for isothermal diffusion. The success of these applications is the most persuasive evidence for the correctness of his initial postulates, especially the regression hypothesis. The argument completes its journey, starting from the abstract symmetry of microscopic time and ending with the successful prediction of measurable coefficients in a laboratory setting. This demonstrated predictive power solidified the importance of his work, transforming it from a theoretical curiosity into an indispensable tool for the physical sciences. In conclusion, Lars Onsager's 1944 Nobel lecture stands as a masterwork of physical reasoning, presenting a fully formed and remarkably coherent argument for the fundamental nature of reciprocal relations in irreversible processes. A systematic evaluation of its internal claims reveals a structure of exceptional intellectual integrity. The lecture builds its case meticulously, beginning with the foundational claim of microscopic reversibility, translating it into a statement about statistical correlations, and then bridging it to the macroscopic world through the ingenious postulate of the regression of fluctuations. The subsequent derivation of the symmetry L sub ik equals L sub chi is logically sound, and its refinement, in the presence of magnetic fields, demonstrates the theory's depth and consistency. The final validation, through application to established phenomena like thermoelectricity, provides a powerful, pragmatic confirmation of the entire edifice, the enduring significance of the work, as articulated in this lecture, lies in its successful construction of a bridge between the two great pillars of physical thought, the reversible mechanics of the microscopic realm and the irreversible thermodynamics of the macroscopic world. Onsager provided a rigorous, generalizable framework for understanding coupled transport phenomena, establishing the bedrock for the modern field of non-equilibrium thermodynamics and demonstrating with unparalleled elegance how the deepest symmetries of nature constrain the complex tapestry of observable reality.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.